Hey, we're looking at the topic of optimization. This corresponds with section 4.7 in our textbook. So, optimization is really something we've done before. It's finding maximums, minimums that help us, but they're kind of caged in the story problem. So you have to kind of read it out what you're really optimizing, finding the maximum or minimum of. So that means you're using an equation that we're taking the derivative of and all that to find maximums. But sometimes to do that, you need to also use a secondary equation. So think about like solving systems of equations using substitution. Using another secondary equation to substitute into the primary equation, the one you want to optimize, and then finding the maximum and minimum of that. Alright, so let's look at a few examples, work all the way through them, then have you try the others after I provide the setup for you, okay? So, optimization, you're finding a maximum or minimum. So let's look at example 1. Find two positive numbers that minimize the sum. Now right there. Okay, minimize the sum. That tells you that you want to optimize a sum equation. So our primary equation, let's call that S for sum, twice the first number plus the second. So twice the first, let's say 2x, plus the second. So plus y. And that will be our, can move this over a little. Okay, here, move over. From here, you're going to be room to write primary. Because that is what we're finding the minimum of. We're going to optimize that equation. So we're going to find ds. Now the product of the two numbers is 288. So it gives us another equation to work with, one that we're not optimizing. That would be our secondary equation. So the product is 288, so product multiplying x times y is 288. So solve this equation for y. So divide both by x. Y equals 288 divided by x. And then use that, substitute it into your primary. So plug that in for y. And I want to write it down here though. It's kind of sloppy, not going in a very linear path, kind of skipping around. But our sum is 2x plus, and we're going to take the derivative, so I'll say 288x to the negative first. Just with that little rewrite of that equation. So then take the implicit derivative. And we're taking it with respect to x. So ds dx equals 2 minus 288x to the negative 2. So that'd be 2 minus 288 over x squared. Alright? So, you're finding a maximum such that they equal to 0. Then go ahead and solve. X, or 2 equals 288 over x squared. X squared equals 144. Take the square root, x equals plus minus 12. But they said two positive numbers in the start of the problem. So you don't want the negative. We only want the positive 12. So you have x is 12, y is 288 over 12. So y is 24. You have x, and you have y. Then, of course, do yourself a favor, check out those in your equation to make sure they work. They satisfy one or both of them, okay? So really, finding your maxes and mins, you've done that before, but now it kind of reminds me a little of relative rates. You're gonna find an equation you're gonna optimize. They give you hints of what they want you to use, and then they give you, or you readily know, secondary equations you could use in order to take an easier derivative. Let's look at example 2. So an open box is to be made by a piece of metal, 16 by 30, cutting squares out of every corner, but name the size. What size square should be cut out to create a box with the greatest volume? So right there, with the greatest volume. And then they come on to say it in the next sentence. What is the maximum volume of the box? So I think we have our primary right there. Gonna be a volume. So primary volume is length times width times height. Alright? And now, do we have a secondary? I don't think we do. We're going to want to do some substitutions for L, W, and H, so that you could think of those as secondaries. But I don't think you have one like we did in the first example. Okay? So our length, let's say length is right here. Width, let's say width is here. Height is however big a square you cut out to fold up. So the size, the height of the box, is dependent on how big a square you cut out. You cut out a small square, it's a small height folding up. Cut out a big square, bigger height folding up. So H is right there. H is X. For the length, that would be the total 30, but to take an X from both sides. So 30 minus 2X. Width, kind of the same idea, 16, but then you're taking 2X's out of it, and our height is X. So if you wanted, you could do product rule, a triple product rule, and you could try, or you could distribute first and then do a power rule instead. So doing some distribution, 30 times 16 is 480. Minus 30 into x is negative 60x. 2 and 16, negative 32, so negative 60, negative 32. Right, just making sure my math is good, negative 92x. And then 2x and 2x, negative 2x, negative x, give you 4x squared. So doing that multiple distribution or double distribution, and then just distribute the final x into the problem. So our volume in the end is 4x cubed minus 92x squared plus 480x. And you might hear some thunder from outside. The video's gone kinda dark. Could you see a light of the iPad shining me a little? Oh no, what did I do? Okay, there we go, we're better. So then take the derivative. dv dx, derivative with respect to x. So bring the 3 down, 12x squared. Bring the 2 down, 92 times 2 is 184x and 480. And we want to do a maximum of this, so we want to have the derivative equaling 0. So every term, 12, 184, 480, they're all, I think, divisible by 12. Check in 184. What's not? Oops, my bad. They're all divisible by something other than 12. I think, boy, my mental math. Okay, it is 4. 184 can be divided by 4. So, cancel the 4 out of your term. 3x squared minus 46x plus 120. So got a little more room. Let's factor that down. So 3x and x. So two numbers that multiply to 120, but then when one of them is multiplied by 3, they add up to 46. They're both going to be negative because they multiply to positive 120. So in my mind, it's kind of like a guess and check method. So you got like what two numbers multiply to 120, and I look like a ghost. Wow. Okay, so two numbers that multiply to 120, when one of them is multiplied by 3, they would add up to 46. So I'm thinking 10 and 12. So 10 times 12 is 120, negative 10, negative 12, add multiple to 120. 3 and negative 12 is negative 36. 10x, negative 10, those would add to 46. Right, zero product property says both equal to 0. X equals 10/3 or 12. Those are the two x values where the derivative equals 0. But look at your box. It's only 16 wide. If you took 12 from both sides, you can't. There's not enough metal. So that 12 is not going to work. So our volume, which is 30 minus 2x, and for x, plug in 10/3. And then 16 minus 2x, x is 2/3. And all of that is then multiplied by 2/3. So we have 2 times 10/3, that's 20/3. And the 30, let's just get a common denominator with the 20/3, so 90/3. there's 2 times 10 thirds, again 20 thirds. Let's get that common denominator with the 16, so that's 48 thirds. And you have that other 10 thirds at the end. So we have 70 thirds, 48 minus 20, 28 thirds, and another 10 thirds. So 70 times 28, 70 times 28, so 70 times 20 and 70 times 8. Then add them together. So 70 times 20, 1400. 70 times 8 is 560. So 1400, 560 is 1960. I think I'm right. Let me check. Heyo, still got it. Okay. Then the bottom times the bottom, 3 times 3 is 9. That's times 10 thirds. So then multiply it again. 1960 times 10 is 19,600. 9 times 3, 27. And 19,600 divided by 27 is about 725.926. And this is inches cubed. So F for Q, leave it at the fraction. If it's calculated a portion, give the decimal, but if you want to, give correct to 3 decimal places, okay? Every year seems students forget they only go to 2. Please go to 3, okay? Alright, so 2 optimization problems. For the other 3, let's kind of give you a setup for these. So, you're unfortunately swimming in the ocean a mile from shore. How you got out there, who knows, but you should feel bad about your choices to get you out there. You want to get to a town that's 3 miles away. A coast is really rocky. Boy, 3 miles, just get a boat, jeez. What point should you swim to the 2 along the shoreline so that the time it takes to get to the town is a minimum? So our time. Under time to be a minimum, because are you gonna swim here and go there to the town, gonna swim here, go to the town, gonna swim here, go to the town, what you gonna do? So our primary equation, what we want to find is time. Okay. Our total time of the entire trip. I think there's going to be quite a few secondary equations to this. So starting with this right triangle here, okay? Gonna use some different colors here. So our distance would be square root of 1 squared plus x squared. Kind of looking at that right triangle. Our distance, if I can get over here, d, that's a bad d. D, just Pythagorean theorem, okay? Now with us traveling, we also have to consider distance equals rate times time. So d equals r times t. And then we have d. Square root 1 squared plus x squared equals, when we're in water, we swim at 2 miles per hour. So our rate is 2 times time. So our first time, let's call this time sub 1. That's the time in the water. It's root 1 squared. Why do I do that? Just 1. Plus x squared over 2. And we'll call this d1 also. And r1, why not? Now our secondary equation is going to be if once we get to land, how far we gotta walk. Okay? So the whole distance is 3 minus x minus however far we go diagonally towards the shoreline. So the whole distance 3, take away the x. So d2, 3 minus x. Now distance is still rate times time. So then plug everything in that you know. So d2, 3 minus x. Our rate or speed on land, that's 4 times time sub 2. So time sub 2 is 3 minus x all over 4. Now our total time for the whole trip is how long we're in the water, t sub 1, and how long we're on land, t sub 2, added up. So we have t sub 1 here, t sub 2 right here. So our total time is root 1 plus x squared all over 2 plus 3 minus x all over 4. So then go ahead, take the derivative, set it to 0, solve, find your x value, how far on the shoreline you want to swim. Example 4, find the dimensions of the largest area rectangle. So that's our optimization, the area. So let's go primary. Look in the area, so A equals x, y. Now look at this circle, okay? We need a secondary equation that relates to the rectangle inscribed in the circle. The circle has a radius of 4, so it has a diameter of 8. The rectangle should fit in there with right angles. So x squared plus y squared equals 8 squared. So x squared plus y squared equals 64. Let's go ahead and solve that for y. So y squared equals 64 minus x squared. Square root y equals square root of 64 minus x squared. Go ahead, take your y, plug it in. So our area equals x times root x squared, root 64 minus x squared. So when you find derivative, you need to use product rule for that. Find derivative, so equal to 0, all that good stuff. Example 6. Kind of the setup here. So which points to the graph of y equals 4 minus x squared are closest to the point 0, 2? Are closest. So we want to find how close something is. We're going to be optimizing, specifically minimizing a distance formula. So distance equals square root x2 minus x1 squared plus y2 minus y1 squared. But do yourself a favor. You already have coordinates. Let's call these x1 and y1. So kind of substitution things in. x2 minus x1, which is 0. So we'll call that x squared plus y2 minus y1. That's y minus 2 squared. And now secondary equation, another equation that fits into the problem, which you have right here. Okay, the equation of y equals 4 minus x squared. So go ahead, substitute that in. So 4 minus x squared going in for y. I figured, I'm like, where am I going? Right here, okay. So d equals square root of x squared plus quantity 4 minus x squared minus 2 squared. So that is x squared plus 4 minus 2. Okay, so 2 minus x squared squared. And go ahead and fill this out. Kind of make what's under the radicand easier to work with. So x squared plus 4 minus 2x squared plus x to the 4th. And combine like terms, x to the 4th minus x squared plus 4. Oh, I'm sorry, I screwed up. I'm like, something seems wrong. Okay, that should be a 4x squared. So minus 3. So you want to do the derivative of that. But think for a moment. If you're going to do a square root, okay, the square root of 3 is always less than the square root of 5. Square root of 5 always less than the square root of 9. So what's under the radicand makes the square root smaller. So you really only need to find the derivative of the radicand. Alright? Go ahead, take a look at that, then check your answer with my complete notes online.